So, today we will discuss infinite series of real numbers. We have already discussed the sequences and various concepts regarding the sequence. So, today we will talk about the infinite series. We define normally when we say if a set of element x 1, x 2, x n are given a sequence, when they are added or subtracted and put it in the form of x 1 plus minus x 2 and like this, then we call it a series. But that is not a authentic way of defining the series, because it does not show anything whether the limit convergent or divergent, whatever. So, we define the series as follows: if x, which is a sequence of real numbers, x n is a sequence in R means set of real numbers, then the infinite series generated by x is this terms sequence x n is the sequence S of partial sum x k defined by S 1 is the first term, say x 1, S 2 is the sum of the first term, that is S 1 plus x 2, S 3 is S 2 plus x 3 and so on. So, S n will be or S k will be S k minus 1 plus x k, that is x 1 plus x 2 plus x 3 up to x k. The number x k, the numbers x k or x n, these are called the terms of the series and the number s k are called partial sums, partial sums of this series. This S k means sum of the first k term of the series and so on. Now, if the limit of S, that is the limit of S k when k tends to infinity, if this limit exists, then we say the series is convergent. And has the sum S. We denote the series as sigma x n is 1 to infinity if first term is x 1, or sometimes we also denote like x n without the suffix, that shows that summation is taken from 1 to infinity. So, this is the way of defining it, or some other, if the first term is starting from x 0, then the summation will be taken from 0 to infinity and like that. And if the series whose first term is say x 100, then the series will start from n equal to 100 to infinity. So, that way we can identify them. Okay. Now, if this limit does not exist, then in that case we say the series diverges. If the limit S k when k tends to infinity does not exist, it means either it is infinite plus infinity or minus infinity or has a various limits does not exist, then we say then we say the series sigma x n 1 to infinity diverges. Okay. So, that is the, for example, we have a series, suppose we have the series sigma r to the power n, n is 1 to infinity. Now, that is the series 1 plus r square and so on plus r to the power n like this. So, this is the series. Now, we claim if mod of r is strictly less than 1, then series converges. And the sum of the series and sum is equal to 1 over 1 minus r. Sum will be this. But if r is equal to 1, if r is mod r is greater than or equal to 1, then the series diverges. The proof is very simple. Solution. Let us find the first sum of the first n terms. So, let S n is the sum of the first n terms 1 plus r square plus r to the power n. This is the sum of the first term r n minus 1, because this will be first term, second and up to n terms. Okay. Then if I multiply this by r, then what happen, r times S n, this is equal to what, r plus r square plus r n minus 1 plus r n. Now, I subtract it. So, this implies that 1 minus r S n, when it subtract it, it get cancelled in that, and we get finally 1 minus r to the power n. So, what we get it is S n becomes 1 by 1 minus r to the power n over 1 minus r. Okay. So, consider mod of S n minus 1 over 1 minus r, that is equal to mod of r to the power n over mod 1 minus r. Now, r I am choosing fixed, but it is less than 1. If it is less than 1, this term will go to 0. So, this tends to 0 as mod r is strictly less than 1. Therefore, the limit of this S n as n tends to infinity is exist and equal to 1 minus r. So, this series converges and converges to the sum 1 over 1 minus r. For r is equal to 1, obviously, the terms are 1 plus 1 plus 1 and so on, so up to S n will be n. So, when n is infinity, limit S n will tends to infinity. So, it will diverge. For r greater than 1, we will see in due course that it also diverges. In fact, it will limit will not exist and it will go to infinity. So, that we will come and obviously, we can find out the sum. Clear? So, this is very interesting one. Similarly, another examples, this part we will take up after going for the further tests, then we say automatically by pth test it will come diverges. And then let us take this sum, this series sigma 1 over n plus 1, n is 1 to infinity, we claim this converges and sum is 1. The solution is again simple. if I take the terms S n, what happened? This term are S n are 1 over 1 into 2 plus 1 over 2 into 3 plus 1 over up to say n is 1 into n plus 1. So, this will be, if we write it in the form, since 1 over k plus 1, we can break up and put it in the form of 1 over k minus 1 over k plus 1. So, using this, each term we can put it in this way, and once you put it this thing, then S n becomes, this is 1 over 1 minus 2, that is 1 over 1 minus 1 by 2, this will be then 1 by 2 minus 1 by 3, like this 1 by n minus 1 by n plus 1. So, get cancelled and finally, you are getting 1 and 1 minus 1 over 1 plus. So, S n becomes 1 over 1 minus 1 over 1 plus n, all n plus 1. Now, as n tends to infinity, it goes to 1 minus 0, that is goes to 1 as n tends to infinity. This term will go to, as n tends to, this will go to 0 and this is 1. So, the limit of this exists and equal to 1. So, this way we can identify that. So, these are few examples. Now, in case of the convergence series, there is a necessary condition that if a series is convergent, then its nth term will always go to 0. That is a necessary condition for us. So, if a series whose nth term does not go to 0, the series cannot be a convergent series. So, that is the criteria which we have, the necessary condition, for convergence of this series sigma a n is 1 to infinity. So, this we will put it in the form if the series sigma x n, we are doing with x n. So, let us put it x n, sigma x n, n is 1 to infinity, converges, then limit of the x n must go to 0. Limit of x n as n tends to infinity will be 0. That is, any term will always go to 0. Okay. So, of proof, let us see the solution or proof. So, what is our S n? S n basically x n, this is nothing but what? S n minus S n minus 1, because S n is the sum of the first term, where S n stands for x 1 plus x 2 plus x n. So, S n minus 1 means up to x n minus 1. So, when you subtract, you are getting S n. Now, this series is convergent. So, limit of the S n will exist. So, limit of S n and limit of S n minus 1 will be same. So, therefore, limit of x n when n tends to infinity, this will be the limit of S n minus limit of S n minus 1, but both the limit will be the same. So, it will come out to be 0. So, this is the necessary condition for a series to be convergent, but this is not a sufficient condition, but this is not remark, but this is not a sufficient condition. That is, if at any term of a series converges to 0, then it may or may not be a convergent series. For example, suppose I take this series sigma 1 by n, n is 1 to infinity. Here x n is what? 1 by n, which tends to 0 as n tends to infinity. And this we have seen that this series and but the series S n, this series sigma 1 by n 1 to infinity diverges as we have seen earlier, because it is a harmonic series. In fact, the proofs we have gone already seen, because the if you remember, we got the S n to be 1 plus 1 by 2 plus 1 by 3 up to 1 by n, is it not? And then it keeps on increasing. When you take the n, then it keeps on increasing. In fact, limit of S n will go to this keeps on increasing, okay, diverges. So, this we have already increasing functions like this and keeps on like unbounded one. So, this we are not already shown in the first lectures while going for this series sequences. In case of sequence, this example we have taken and shown the series diverges. So, here this diverging. If we take another example, say sigma of 1 over n square 1 to infinity. Now, here the x n, which is 1 by n square, goes to 0 as n tends to infinity, but this series converges. What this series converges, that will also be shown in the next few after few article to be covered. When test for the series is there, then this is 1 upon sigma n to the power p type, where p is greater than 1, series will converge. So, that we will prove it, hence from there you can say this is convergent. But what is the you see that these two series, in both the series the nth term goes to 0, here also it goes to 0, but one series diverges, other converges. So, the taking the sequence x n, the nth term, checking whether it is tending to 0 or not, this will not give a conclude either. Just tending to 0 will not implies the series is convergent, because it may be divergent also. However, if we take the any sequence x n, any series x n whose nth term does not go to 0, then series has to be a diverging series, because if it is convergent, then correspondingly the nth term must go to 0. Okay. So, that is why here this will third point remark, if in the series sigma x n 1 to infinity, the nth term of positive term sigma x n a series, if the x n is a sequence of terms, if the limit of x n when n tends to infinity does not tends to 0, then the series diverges, then the series sigma x n 1 to infinity diverges. And the reason is very simple. The reason is why, because if it is convergent, then according to the necessary result earlier, the necessary condition for a convergence of the series, the nth term must go to 0. So, this is not happening, therefore, it will diverge. So, if the series of positive term, let us take the positive, because series of positive terms also, positive terms, okay, where this goes. So, this was part of it. Okay. Now, there is another result, just like a Cauchy convergence criteria. We have a Cauchy convergence criteria for the sequence. Any sequence of real number is convergent if and only if it is Cauchy. That is, it satisfies the Cauchy convergence criteria, that after a certain stage the difference between any two arbitrary terms of the sequence is less than epsilon, given epsilon, then we say the sequence is convergent. So, correspondingly we also have a result for a series, that is known as the Cauchy convergence criteria for series. So, next is Cauchy convergence criteria for series. The result is the series sigma x n 1 to infinity converges if and only if for every epsilon greater than 0 or for given epsilon greater than 0, there exists a positive integer n, there exists a sequence as there exists a positive integer capital M which depends on epsilon such that for all m n greater than or equal to capital M, the following condition holds: the mod of S m minus S n, the partial sum of the series mth term up to mth term and up to nth term is less than epsilon for all n. That is equivalent to say is that mod of x n plus 1, if I choose m is greater than n, if m is greater than n, then x n plus 1, x n plus 2 up to x m is less than epsilon. That is up to here. So, this is known as the Cauchy convergence criteria, and this part is if and only if, that is if the series converges, then sequence of its partial sum will satisfy this condition. Clear? And obviously, we have defined the convergence of the sequence as when the limit of the Sm goes to limit exists. So, when the limit of the sequence of partial sum exists, then only we say the series converges. So, suppose the series converges. So, limit of Sn exists. It means the limit of Sn exists means it must satisfy the Cauchy convergence criteria. So, this is nothing but the Cauchy convergence criteria. And conversely, if this is true, then the limit of the sequence Sn must exist. Limit of the sequence Sn exists means this series must be a convergent one. So, that shows the connectivity. Okay. Now, based on this, we have a very interesting results. The result is in the form of theorem. Let x n be a sequence of non-negative real number. Real numbers, then the series sigma x n 1 to infinity converges if and only if the sequence of partial sum S of partial sums sequence S of Sk of partial sum is bounded. Okay. And in fact, when it is bounded, the limit superior of this limit of Sn will come out to the sum of this. So, let us see the proof of it. Okay. What is given is the sequence x n is a sequence of non-negative real numbers, positive numbers. Okay. Non-negative maybe 0. The series is convergent if and only if the sequence is of the partial sum is con. So, suppose the series converges, it means limit of the Sn will be exist. And what is our Sn? Sn is basically the partial sum. S1 is the first term, S2 is the sum of the two terms 1 and 2, and since x1, x2, xn are non-negative real numbers. So, maybe few may be 0 or maybe strictly greater than 0 also positive number. So, S1 definitely less than equal to S2, which is less than equal to S3 and so on like this. So, what we are getting is the sequence of the partial sums. So, the sequence of partial sums sequence of partial sums is a monotonic sequence of increasing numbers, increasing monotonic sequence increasing monotonic sequence of real numbers. Okay. Now, what is the monotonic convergence theorem? Monotonic convergence theorem says any monotonic sequence which is either increasing or decreasing, and if it is bounded, a monotonic sequence which is increasing and bounded above, then it must be convergent, or monotonic sequence which is decreasing and bounded below must be convergent. Here this is a monotonic sequence, increasing sequence of real numbers, and what is given is a series is convergent. If this sequence is given to be bounded, suppose I take this part, if sequence is bounded, then it means this monotonic sequence is bounded. So, once it is bounded, it has to be convergent. Okay. So, if the sequence S k is bounded, then by monotone convergence theorem, the sequence S k is convergent, that is limit of x k exist. In fact, it is the upper bound for this. It is the supremum value of all S k's when the k belongs to integer. Supremum value, it is upper bound for this. We have not discussed upper bound, we will take up after that. Okay. In fact, this limit. So, if the S k is bound, partial sum is bounded, then we can immediately say by monotone convergence theorem, this limit will exist, hence the series is convergent. So, this implies the series sigma x n 1 to infinity converges. Conversely, if given the series sigma x n 1 to infinity converges, it means what? That means the limit of this sequence S k over k exists finite. Now, every convergent sequence is a bounded sequence. So, this means that sequence S k is convergent. So, it is bounded. So, this proves the both way, that if this series is convergent, then the sequence of the partial sum will be bounded sequence, and vice versa, if sequence of the partial sum is bounded, then the corresponding series will be convergent. So, that is the convergence criteria for that. Now, if we look that series, that what we are talking about, we have seen this example sigma r to the power n 1 to infinity, and we have seen that this series converges if mod r is less than 1. Okay. But if mod r is greater than or equal to 1, then what happens? What is our S k? S k becomes 1 plus r to the power k minus 1. Now, this each one is greater than 1. So, it is greater than k, is it not? Because it is greater than 1. So, limit of S k does not exist, unbounded. Therefore, S k sequence is not bounded. Okay. So, this series cannot be convergent, because if it is convergent, the sequence of the partial sum must be bounded as per this result. So, this shows the series r to the power n 1 to infinity diverges if mod r is greater than 1. here we are taking one more thing is, here we are taking all the terms of the sequences to be non-negative. We cannot apply this result for the series whose terms are, some are positive, some are negative, like this. We cannot apply this result, or we cannot do for the non-negative terms. If all the terms are negative, what we can do, we can take the minus sign outside and make it all the term to be positive. But if the series is alternately positive negative, then of course, this result is not helpful. Its result is only valid when the terms of the series are all non-negative. So, here when we are taking mod r is greater than 1, basically we are choosing all r to be greater than 1, positive. This is positive. So, r is greater than 1, taking r to be greater than 0, all positive, then this diverge, and r is equal to 1, obviously again we take 1 plus n. So, S n diverges, therefore, it unbounded, therefore, it is not convergent. Okay. Similarly, for this. Now, we have another results which is also very testing, and that result is, yes, this next result which will help you in driving the few more results. This result is in the form of theorem. What this result says is, suppose x 1 is greater than equal to x 2 is greater than equal to x 3 is greater than equal to, all terms are greater than equal to 0, means non-negative terms. Then the series sigma x k or x n, n is 1 to infinity, x n 1 to infinity converges if and only if the series, sigma k is equal to 0 to infinity 2 to the power k x 2 to the power k x 2 to the power k x suffix 2 to the power k, that is a series is x 1 plus 2 times of x 2 plus 4 times of x 4 plus 8 times of x 8 and so on. This series converges. Okay. So, this is very result which will help in driving the few more results with the help of this. So, this is the proof. Let us see. What he says is, suppose a series sigma x n is given whose all terms are non-negative, then the nature of this series, that is a series will be convergent if the corresponding this series will converge and vice versa. Okay. So, in order to test this series to be convergent, you convert this series into this form, which will be more comfortable in a suitable form, which can easily be proved to be a convergence or divergence. So, corresponding nature of this, if it is convergent, this will converge. Okay. That is what he says. Okay. So, let us consider the partial sum. Let S n stands for the partial sum of the first series, say x 1 plus x 2 plus x n, and let T k stands for the partial sum of the second series x 1 plus 2 times of x 2 plus 2 to the power k x suffix 2 to the power k. Suppose we are taking this term up to say 2 to the power k, 2 k, there are few gaps, is it not, because it is not in continuation, x 1, x 2, then after that x 3 is missing, x 4, like this. So, we are choosing this term. Now, let us take the different cases. For n which is strictly less than say 2 to the power k. Then what happen the Sn, this will be less than or equal to x 1 plus x 2 plus x 3. If we combine this and then let us write this form x 2 k 2 to the power k plus x 2 to the power k plus 1 up to say 2 to the power x 2 to the power k plus 1 minus 1. Say I am taking x n to be less than this number. Obviously, when I am taking n is less than 2 to the power k. So, obviously, these terms which we are taking is much higher than this, okay? And total terms in this case will be what? Now, this will be x. Now, x 1 is greater than x 2, x 2 is greater than x 3. So, basically, this will be x 2 is greater than x 3. So, we can say this is x 3 is lower than x 2. So, it is less than 2 of x 2. So, this will be less than x 1 plus 2 times of x 2. Similarly, when you go for x 4, x 5, x 6, x 7 and x 8, then we will get next term will be 4 less than x 4, okay, that term, and continue this. What will happen to this? There are only 2 to the power k terms. So, 2 to the power k into x 2 to the power 2 k. This will be, because this is the smallest term and this is the largest term and rest are decreasing, is it not? So, it will be less than this, but this term is nothing but what? T k. So, what we get is that S n is less than equal to T k, okay. This is one thing. Now, for n, let us take n to be strictly greater than 2 to the power k, and then again you rewrite suitably. S n can be written as greater than equal to x 1 plus x 2, and then combine this term x 3 plus x 4 like this, and last term start with the x 2 to the power k minus 1 plus 1, this term, and up to go x 2 to the power k up to this. So, what happen is this is greater than equal to. Now, let us write x 1 is obviously greater than half of x 1, is it not? Because it is positive term. Then plus x 2 remain as it is, then x 3. Now, x 3 x 4, x 3 is less than x 4 or x 4 is greater than. So, if I replace x 3 by x 4, then it is greater. So, it is greater than equal to 2 times of x 4, 2 times of x 4, this will be, yes, is it not, 2 times of x 4 and like this up to 2 to the power k minus 1 into x 2 to the power k, like this, okay. So, x 3 is greater, x 3 is greater like this. Now, you check it, this will be what? If I take the t k is coming to be x 1 plus 2 x 2 plus 4 x 4 like this. So, it is half of this. So, basically it is the half of t k. So, what we get from 1 and 2? We get from this. So, from 1 and 2 we get from 1 and 2, what we get is that S n is less than equal to T k and S n is greater than equal to T k by 2. But what is T k and S n? Let us say, let T k and S n, the S n is the partial sum, nth partial sum of the series sigma of x n, and T k is the partial sum of the second series sigma 2 to the power k x 2 to the power k. Now, these partial sums satisfy this condition inequality. So, if T k is bounded, S n has to be bounded. Now, if S n is unbounded, T k has to be unbounded. So, this implies the third criteria implies that the sequence S n and the sequence T k are either both bounded or unbounded or both unbounded or both unbounded. That is it. So, once they are unbounded, the result follows. It means the nature of this series converges if only this converges. So, if they are bounded, then they will. So, this implies the series sigma x n converges if and only if sigma 2 to the power k 0 to infinity, here 1 k is equal to 1 to infinity, it's okay, n should I write, it's okay, sigma 2 to the power k x 2 to the power k converges. Okay. So, this what we get it, and this should be right n, because otherwise that will be different. Okay. So, n is 1 to converges if only this comes, and this completes the proof. Okay. So, this comes. Now, as a corollary to this, or as a particular case, cases, okay, we have this result theorem in the form the series sigma 1 by n to the power p, n is 1 to infinity, converges if p is strictly greater than 1 and diverges if p is less than or equal to 1. Okay. So, this we get. Let us see the proof of this. It will follow from the previous results. Now, obviously, if p is less than or equal to 0, suppose p is 0, then what happens? This each term becomes 1. So, each term becomes 1 means the nth term will not go to 0. So, when p is 0, so in this case the nth, the x n, which is 1 by n p n to the power p, will not go to 0, because when p is less than equal to 0, this will come in the up and it will not go to 0, it will diverge, because p is negative or 0. So, by necessary condition does not satisfy. Therefore, the series sigma 1 by n to the power p 1 to infinity diverges if p is less than equal to 0. Okay. Now, take that case when p is strictly greater than 0. So, if p is strictly greater than 0, then what we claim is when p lying between 0 and 1, even 1, it will diverge, and when p is greater than 1, it will converge. Okay. So, now apply this result. By the previous result, by previous theorem, the two series will have the two series, the series sigma 1 by n to the power p 1 to infinity, okay, and the series sigma k equal to 0 to infinity 2 to the power k 1 by, replace n by 2 to the power k, 2 to the power k power p, because n to the power p I am replacing n x n by this, x n is 1 upon n to the power p. So, replace n by 2 to the power k. So, n to the power p, this two series, so the series will have same nature. That is, if they are, if this is convergent, it has to be converged, and vice versa. If this is convergent, this, and similarly divergent part. Okay, will have the same nature. But what is this? The series, but the series sigma k 0 to infinity 2 to the power k 1 by 2 to the power k p, k into p. This is nothing but what? This is equivalent to sigma k equal to 0 to infinity 2 to the power 1 minus p into k. Okay. Now, this is basically a geometric series. This is a geometric series. So, if we take, if 1 minus p, if 1 minus p 2 to the power 1 minus p, if this part is less than 1, strictly less than 1, then it will behave as a geometric series sigma 1 r to the power k, where r is, mod r is less than 1. So, this will be this series, then it means that is what, when it is less than 1, when 1 minus p is negative, that is p is strictly greater than 1. So, in this case the series say fourth, if this, then the series fourth behaves as a geometric series of the type of the form sigma r to the power say k, where k is 0 to infinity and r is greater than 1, r is, sorry, less than 1, because r is less than, r is this term. So, in that case it converges. So, the given series sigma k equal to 0 to infinity 2 to the power k 1 by 2 to the power k power p converges if p is strictly less greater than 1, and if p is less than, if this thing is greater than 1, obviously then greater than 1. So, it is the limit of the nth term does not go to 0, therefore, it diverges. When equal to 1 also it will diverge. Okay. So, this shows, otherwise, and obviously for p less than or equal to 1, the series diverges. Hence, the corresponding series sigma 1 by n to the power p, n is 1 to infinity, converges if p is strictly greater than 1, and diverges if p is less than equal to 1, and that proves the result. Now, when p is equal to 1, it is a harmonic series and it diverges, that what we show. When p is equal to 2, it is convergent, and the example which we have chosen, that necessary condition x n tends to 0 is not a sufficient condition, is justified from here. Okay. So, that now, based on this we can also say another example, let us say, suppose, or result, because this will also be useful if p is greater than 1. If p is greater than 1, then the following series converge. Then number 1, sigma n equal to 2 to infinity 1 by n log n to the power p converges. Log n to the power p converges. Okay. when p is greater than 1 converges, and if and otherwise diverge, and if p is less than or equal to 1, then the series 1 diverges. Again it follows from the same thing. If you go through that one, then the follows the same thing. How the solution will come? To test the sigma x n convergent, what we do is we find out the 2 to the power k. So, the series sigma 1 by n log n to the power p 2 to infinity converges if and only if sigma k equal to 1 to infinity 2 to the power k log 1 by 2 to the power k log 2 to the power k power p. Obviously, when k is 0, we cannot choose because log 1 is 0. That is why we are avoiding that one. This is. So, this converges means if this converges by, but this converges equivalent to what? Is it not the same as 1 by log 2 power p sigma of 1 by k to the power p when k is 1 to infinity, and this series converges, this is convergent if p is greater than 1, because this is the nth power test. So, this series converges. Similarly, if I take the second part, suppose I take this series sigma n is equal to 2 to infinity 1 over n log n into log n into log n, this diverges, while the series sigma n is 2 to infinity 3 to infinity, because this is n is I think 3, because otherwise this 2 will not, n is 3 to infinity, 1 by n log n, then log n 2 power 2 converges, and the reason is the same as above. Okay. So, this thank you very much. Thanks.